Harlem Shake.
Wireless Brains is submitting a proposal for building 2 robots that go into a test nuclear reactor. The robots will be used to move experimental fuel rods from a pallet room into an elevator, which will then transport it down to the actual reactor room. Once in the reactor room, we have another robot that will move the rods into the reactor. The video shows on the right half a view of the entire reactor room. The top left part of the video shows a close-up of the pallet, and the bottom left shows a close-up of the reactor. The robots are required to be in a certain orientation when moving the rod from the pallet or into the reactor and elevator. First, we must create an orientation of the robot that is able to move all of the rods from the pallet and all of the rods into the reactor while staying in the same configuration. To accomplish this task, DH parameters were iterated until we found a set that allowed all paths to be physically possible. Once the orientations were determined for sliding the rods out of the pallet and into the elevator, several points in between those 2 orientations were determined that the robot had to move through while staying within joint limits. Several attempts were made to find the best path between these 2 orientations.
The inverse kinematics were calculated at key points along the trajectory. This was done using the robotics toolbox functions ikine and ikunc. Once we had the joint orientations at these key points, time-dependent trajectories could be generated between them to fill in the points along the path. These time-dependent trajectories were created using the robotics toolbox function jtraj. In order to use the robotics toolbox functions ikine and ikunc, a robot object had to be created with the proper DH parameters and joint limits. The robotics toolbox function ikine utilized the robot object as an input as well as the end effector position and orientation. This was passed as a homogeneous transform. Additional inputs were a guess for the orientation and a mask, which specifies any translations and orientations that do not need to be solved. The function ikunc is very similar to ikine, but no mask input is passed, and optimization techniques are utilized to calculate the inverse kinematics. jtraj generates the time-dependent trajectories between the start and end joint configurations. Default 0 velocity and accelerations are used at the boundaries. The output of jtraj is joint angles, joint velocities, and joint accelerations along the path. In several situations, different techniques were required to calculate the path plan. C trajectory was used to calculate a time-dependent trajectory of homogeneous transforms. Using these homogeneous transforms, the position and orientation of the end effector was controlled through an entire segment of the path. The inverse kinematics was run at each point along this path to generate the required joint angles for that section of the path.
The simulation was created in SimMechanics. All the given models for the room and the joints were exported from SolidWorks to SimMechanics in the form of a step file. The 2 robot models are built with the desired parameters using SimMechanics transform and joint blocks. A time series data is generated from the MATLAB script, and it is fed into the SimMechanics simulation to drive each of the revolute and prismatic joints. Sim mechanics automatically calculates the moment of inertia and the center of mass with the given density and the geometry of the body.
Here is a close-up of the robot placing the last rod into the reactor. We will now show the robot running the reverse path, moving the rods from the reactor back to the pallet room. The reverse path was computed by calculating the trajectory with the points in reverse, but still in the correct order for unloading each rod. While the video shows the robot placing the rods back into the pallet, the control will be discussed. The robot plant is difficult to control because it is highly nonlinear. As the robot moves from configuration to configuration, the dynamics change. This can cause instabilities in a standard PID controller unless different gains are calculated for every possible configuration. Due to these difficulties, our team decided to use a model-based controller where the torques for motion are calculated offline and then fed forward to the controller.
We are experiencing technical difficulties. Your call is important to us. Please hold. We are experiencing technical difficulties. Your call is important to us. Please hold.
Thank you for holding. Okay, I'm going to talk about the control system implementation. First, we created a open loop controller where talks from R&D function are taken as inputs. But the controller performed very poorly and the robot joints were moving in random directions. For the second case, we created a PID controller with feedback system, where position and velocities from the position simulation were fed back into the controller to keep the torques under control. As you can see, the system is under control, but the joints are still wobbling. In the third case, we created a full controller with position and velocities are taken as feedback and the torques were fed forward. So we iterated through PID values to get the robots under control. As you can see, the robots perform a lot better and it follows the path perfectly with almost no wobbling.
This has been a fun project. These are our group members. A special thank you to our robots R1D1 and R2D2. May the torque be with you. This is Luke Skywalker, signing off.